Sam, you're good to go whenever.
Yes. Okay. Excellent. Excellent.
Yeah.
Okay. Hello, everybody. Okay, I think we're just going to go ahead and get started, even though the door's still open. Hi, everybody. My name's Sam Fielder. I am from the University of Victoria. I moved here about 2 years ago. And today I'm going to be talking to you about generally the broad nature of the field that I work in. As an astrophysicist, mainly star formation in general, but more specifically what radio astronomy is and why it's so useful to study stars. Okay. That's a little better. Excellent. Okay, so a little bit about myself. As I said, I'm a second-year master's student here, and my supervisor is actually based out of the NRC buildings just down below in the parking lots here. So what's great about Victoria and astronomy in general is since we have those NRC buildings, there's a whole slew of extra astronomers in the city that can work with students at the university. So not only do all the faculty members can take on students as researchers, but all the researchers themselves on the Hill here can take on students. And so it allows Victoria to be a very big hub for astronomy in Canada. So my research interests and what I'm doing through my master's and my PhD mainly deals with the topic of star formation and specifically these things called dense cores and how they fragment and evolve over time. And so this is kind of what the broad nature of the talk I'm going to give today. Okay. Now, usually I find myself up at the Hill, usually at every star party that's offered here. I'm usually at the Ask an Astronomer table or outside on the deck manning the telescopes. And I like to start with answering one of the main questions I always get when I get chatting with people. There's two main ones that I usually get. One I hate to answer, and it's the typical, what are you going to do with your degree? Or where are you going to go after this, right? I hate answering because I have no idea. All I know is I love learning, and so that's where I'm at right now. But the second question I always get is, how did you get into astronomy in the first place? And so this kind of goes back to when I was in my teens. I moved from Ottawa to Edmonton. And Edmonton is not only a province over from Victoria, but it's also quite high up in latitude, right? It's a fairly northern city. And so what we get with a northern city is if the sun is, very active, we get a lot of aurora borealis. So some of my favorite childhood memories are going out of town, 1 hour, 2 hour drive in the middle of the winter. It's minus 35, minus 38. We bundle up. And so this is probably one of the best viewing events I had as a kid outside. And this is one of my father's photographs. So not only did it influence me to start going down the physics and astronomy pathway, but it also motivated my dad to start up a hobby in astrophotography. So that's kind of where I got my start. So in terms of the general talk today, I want to start off by kind of introducing where the star formation problem exists and kind of dive in from there. So astronomy deals with a lot of different scales, right? Astronomy is such a huge topic, and it's usually broken down, well, what I will break it down into four main categories, okay? So you have what are called the small scale astronomy. These are things within our solar system. So taking a look at heliophysics, which is physics of the sun, things like planet orbital mechanics or the moons around other planets. We also have asteroid astrophysics, so taking a look at asteroid collision mitigation, things like that. And then this general thing about the Oort cloud, this hypothesized sphere around our solar system which harbors a lot of rocky material. Okay, so that's small scale in terms of astronomy. Then you have all the way into the large scale. So this is more or less known as cosmology. So this is dealing with expansion of the universe, interacting dark matter on big scales. And usually these large scale astrophysicists deal with large scale simulation. So simulating the entire matter from the birth of the universe onwards till the day. Okay, now there's this big gap right in the middle, okay, and I've subdivided this into two sections. The first one is the general galaxy section, so usually dealing with galaxies other than our own. So for this, we usually get a lot of studies into galaxy interactions. So what happens when two galaxies come together and smash together? What happens to the stellar populations within? There's lots of studies as well on metallic archaeology, so tracing where the highest numbered elements, so all the metals in the universe, and tracing where those stellar populations lie over time. And then the last domain is usually within the Milky Way, so studying things that are inside of our own galaxy. So these include star-forming regions, that'll be the basis of this talk. We can get very detailed studies on stellar populations because they're so nearby in the grand scheme of the universe that we're able to do detailed studies on stellar populations. And of course, we think we know that every galaxy hosts a black hole in the center. So this is ripe with black hole dynamics and interacting active galactic nuclei in the middle. And so our talk today will be mainly focused on within our own galaxy and in those star-forming regions that are inside the galaxy. Okay, so when we think of the galaxy, this is what we would see when we look up into the night sky if you were in a dark enough environment, okay? And if your eyes were perhaps maybe a little bit bigger than what we have right now, okay? So this is looking towards the center of the Milky Way plane, okay? So right in the middle, we'll harbor the black hole, right? Sagittarius A star. And then on the other panel is facing directly away from the center of the galaxy, okay? Now this is an optical image, so this is what you would be able to see with your own naked eye. And I think this one comes from the Hubble Space Telescope specifically, at least a big combination of images. And our star formation problem actually is in the places in the optical spectrum where it's the hardest to see inside of. So all these very dark clouds that you see spanning across in this disky portion are where all the stars are forming. Okay, so I've labeled a couple of them on here for you. You might recognize some constellation names on here like Orion or Taurus. There's also Perseus and Cepheus over there. So this is where our problem lies. When we study star-forming regions, we study them inside the Milky Way and things that are fairly nearby. Okay, so this is where our problem lies. So the first part of the talk today, I'd like to take you through the 6-step easy bake oven process on how to make a star that's typical. Things like our own star, okay? So I have a few kind of schematic, cartoony things that I'd like to give you. I'll talk about the different ingredients that make up stellar populations and kind of the step-by-step process on which a star gets built up from these clouds of dust and gas, okay? So our first step is we have our molecular clouds, our giant molecular clouds, okay? So our recipe ingredients are number 1, cold molecular hydrogen. Okay, so that's the first ingredient. Now you might be thinking, that's kind of weird. I know stars are hot things, right? We know our own sun is millions of degrees in the center and thousands of degrees at the surface. But what I'm saying here is we actually need the coldest gas to form stars. It's a little bit counterintuitive. And the reason why we need cold gas is because think about what happens to gas as it gets warmer, right? We have individual gas molecules that are bouncing around, and as you heat things up, that's just directly proportional to how fast those things are moving around. So if we have very hot gas and we try and condense them down into very small areas, there's going to be a lot of pushback against that gravitational force, and it's going to end up dispersing back out. So we need very, very cold gas to be able to clump things together so that the star formation process can even begin. Okay, so you can think of this as a density map where the black areas are higher density than the surrounding, but you can also think about this as a temperature map where the black things are much colder than the surrounding areas. Okay. Temperatures are on the scale of around 10 degrees Kelvin. Okay, so very close to absolute zero. Okay, now in terms of giant molecular clouds, there's also another thing that gets looped into this. If you have a big gas population, you usually have a lot of dust with that. Okay, so So what we have with dust is dust also accompanies a large portion of the gas. Now the dust helps build this thing called molecular hydrogen. So if we think of hydrogen in its base form, it's usually one proton in the nucleus and it has one electron orbiting it. But molecular hydrogen is H2. So it's two hydrogen stuck together. Okay, so what happens is that the dust facilitates this sticking action of the hydrogen. So this dust are like organic compounds, they can be carbon, silicates, and what happens is that those hydrogens fly around and they stick to the dust and it helps them make molecular hydrogen instead. So when we take a look for star forming areas, we like to trace out the molecular hydrogen inside that cloud. Okay, so that's step one. You need a bunch of hydrogen, which usually is accompanied in terms of its molecular form and dust. Okay. Step two in the process is gravitational collapse. So the gravity needs to win against the heat that the gas has, and it needs to bring the material down into something much more compact, okay? So what these items are called is they're called dense cores. So this is what I specifically do in terms of my research. I study these objects called dense cores. They're just over dense regions in clouds that have yet to form stars, okay? But you need to bring that material in together for them to start forming something that looks like a star. Okay, so that brings us to step three. Step three is called a protostar. Okay, so it's a couple steps back from being a fully fledged star, but here in this case, you actually have something that has some structure down in the middle. You have some type of core. Okay, and the protostar stage comes with a couple important features. You have this bigger dark gray envelope that material is funneling into this other structure called the disk, this black kind of bow tie looking thing. Okay, so material will infall into the envelope will feed the disk, and the disk will feed the protostar in the center. Okay, so looking at circumstellar envelopes like this, they're really, really bright in the infrared. And so when we look in infrared telescopes, if we see these envelopes, we know we're looking at a protostar. Okay. One of the other iconic features from protostars, however, are these lines going up and down, kind of perpendicular to the disk. Those are outflows. Because that material is crashing down into the disk and feeding the star, what happens is that outflows get shot out perpendicular to the disk. So you see material get ejected top and bottom outside of the disk. So if we look for those outflows, we know we're looking at a protostar in this case. Okay, so that's step number three. Step number four is a little further down. It's a more evolved protostar. We classify these as T-Tauri stars. So we no longer have an envelope. The envelope is completely deteriorated, and you have this big stellar disk structure, or circumstellar disk. Okay, so material will be infalling. It'll hop onto the disk. The disk will feed the T-Tauri star, and here you have even bigger outflows as a response to that. Okay, so that's the T-Tauri star, step number four. Step number five is our pre-main sequence star. So this is the step right before you get to hydrogen burning, or what's called a main sequence star. Okay, so here we usually have no more inflow just due to the amount of outflow that we see. We have some sort of remnant of a disk structure, and what you'll notice that it awfully looks a lot like a planet system. And so these rings of debris that used to make up the circumstellar disk could eventually start turning into planets. Okay? So step number six, we finally arrive at our main sequence star. Okay, this is the longest living stage of a star's lifetime. It lasts for millions and billions of years. Our sun is currently a main sequence star. It's turning hydrogen into helium. And once that ends, then your star usually ends up going into a supergiant, so it'll most likely swallow the Earth. Okay, sorry to be a little bit of a downer, but it is what's gonna be. I'm sure none of us will be alive to see that. Okay, that'll be in billions of years to come. Okay, so that's our 6-step process on how to build a star. A typical star, what your average process is. You start with a cloud, you gravitationally collapse dense cores, you form a protostar, which ends up shooting out material. That core further evolves down into what we know as stars. Okay, so these comic book kind of sketches on what the process is great for students and the general public to know what these things are. but we're here for the pretty pictures, right? So let's see what some of these things actually look like when we observe them out in space, okay? So step number one is the dark cloud core. So if you wanted to know how dark is a dark cloud, it can be pretty dark, okay? So in this case, this is Barnard 68, okay? It's a dark cloud in the Ophiuchus constellation or Ophiuchus star forming region. So you can see it has very defined edges. This is a big patch of molecular hydrogen that has a lot of dust. So what the dust loves to do is it loves to block out visible portion of light. So all the stars that would make up the background are actually being blocked by this big blob. So you can't see inside of it. Okay, so that's step number one. Step number two, you have gravitational collapse, where you form dense cores. And so usually these dense cores are going to be formed in the densest portions of the molecular cloud. And this usually means is that the densest portions are found along what are called filaments. Okay, so if you hear the term the cosmic web, right, everything looks web-like at all scales. This is also true for star formation. So within these clouds of molecular gas, you'll have these kind of stringy spider web-like features, and where you'll get individual cores start forming along the highest density regions. Okay, and again, those cores are the lowest temperature gas out of this structure. Okay, so that's step number two, our dense cores. Step number three is probably the most impressive step. It's the protostellar step. So this is an example of a neat protostar undergoing huge amounts of outflow. So the disk portion would be going tangential or perpendicular to this, and you see the big amounts of outflows top and bottom. So all that gas is being flung out at tens of kilometers per second, and it's lighting up the environment. It's ionizing all the surrounding gas, and it lights up in the visible portion of the spectrum. So some of the most beautiful pictures are going to be of protostellar sources. And then for our final stages here, down at the bottom, we have disk-like structures. So this is one of the most famous disk-like structures that we have detected. This is HL Tau, and this is one of the most famous images being brought out from the ALMA interferometer, something that I'll point out a little bit later. But you can see the remnant of what is going to be a star in the future, along with probably what's going to be forming a planet system around that object. Okay, so that's great. Good, so we have our six-step process on how to build a star. So now I want to change tracks and talk about the second half of this talk is the radio astronomy portion. What does it mean to be a radio astronomer? Okay, so what I'm going to show you here is basically different ways in which you can look at the same thing. Astronomers deal with a wide range of scales that we can study, and those scales just come from different types of light that are being emitted by objects. Okay, so we all know different types of light, like UV light or visible light or infrared light. All of those lie on a big scale from small wavelengths all the way to big wavelengths, okay? So if you were to look at the Milky Way band in the optical portion, this is what you would see here, something analogous to the things that I showed before with those two circle images. However, if you shift what you're seeing and instead look in the infrared, things like the new James Webb Space Telescope looks at, then you're probing different structures. You see different things. And this is because infrared is great at picking out what's hot, okay? So usually what's being pulled out from infrared images are star populations. And since those star populations are densest right along the disk, you can see all of those different stellar populations, okay? However, if we go even further down in wavelength to the very lowest wavelengths, we get into the microwave and the radio end of the spectrum. Okay, so when I talk to people about my research often, I say, I'm a radio astronomer, right? I study stars being born from radio signals. And then they say, you can hear the stars? And I go, not quite, okay? Radio is not sound, right? We might think of it as sound because the interaction that we have with radio a lot of the time is you get in your car and you turn on the radio, right? But radio is light, okay? It's just not light that we see, just like infrared we don't see. Okay, humans output a lot of infrared radiation. This is why heat cameras work, right? Because your body gives off heat and it gives it off in infrared radiation. Well, the same thing with radio. It's just another type of light. So when we look at radio emission, we're looking at, depending on what type of radio emission you look at, you can trace out the most cold gas inside of star-forming regions. So if you notice in the optical images where all of those dark clouds are, it's actually the brightest in this band, and this is tracing radio emission from molecular hydrogen. So what's being blocked out in the optical, you can actually start seeing inside of the cloud. So this is why radio astronomy is quite useful to star formation, because you can see into the cloud itself. It's not blocked anymore. Okay, so an example of that is we have our Barnard dark blob. This is invisible light. However, if we just take a little step into the infrared, it becomes a little bit more transparent. So you can start picking out the background stars. So this is why shifting in terms of another wavelength is so important for different branches of astronomy. Okay, it turns out that this cloud actually isn't undergoing any star formation inside. So what you're seeing are just background stars. But if there was any star formation inside, you would start being able to pick that out with infrared. Okay, and the same thing goes with radio. You're just going down in terms of wavelength. Okay. So what do radio telescopes actually look like? So I have an example here. This is the 64-meter Parkes telescope in New South Wales, Australia. This one specifically was used for communications with the Apollo astronauts as they landed on the moon, which is quite neat. But here I want to briefly talk about what sets the science and what telescopes you need to do different science. Okay? Now don't be scared. I know this is an equation, and probably nobody really likes math that much, okay, I get it. But I'll walk you through it just to tell you about what sets people when they want to pick a telescope to do their science, okay? And it's all about how much detail can you pull out depending on how far away your object is, okay? So the left-hand side here, this theta, is the resolution, okay? So how finely detailed can you see something, okay? So the smaller the theta, the easier it is to pick out two sources that are nice and close together. Okay, now what affects the resolution? Well, there's D on the bottom here, and that is the diameter of your telescope. So bigger telescope, better resolution. That makes sense. That's why we like to have big telescopes, is because not only do we collect more light with the bigger telescope, we can easily differentiate sources with a bigger telescope, okay? But notice that we have something else in our equation, this lambda. This is the wavelength, okay? So if you go from optical, which is in the nanometer range, because what our eyes pick up, red, blue, green, right? And you go into the radio, that's much longer of a wavelength. Radio is in the centimeter or the millimeter or the meter even, okay? So what happens is naturally, if you go to longer and longer wavelength, your resolution naturally decreases, okay, which is not a good thing. So the way to combat this is if you want the same amount of resolution, but you change the wavelength to be something much larger, you have to now make a bigger telescope, okay? You have to balance that out with the diameter of your telescope, okay? So some of the biggest radio telescopes in the world are, I think the number one right now is in China. It's a 500-meter telescope in diameter. It's in a natural depression in the Earth, and they've built a big parabolic meter there. Okay, so what can you do without making a bigger telescope? Well, what you can use is this fancy technique called an interferometer. So instead, what radio astronomers do is instead of making bigger and bigger telescopes, which usually cost a lot more money, okay, what we do is instead use two smaller telescopes, but we space them out. So instead of the D being the distance or the diameter of your telescope, D now becomes the separation between the two antennas. Okay, so you can make much smaller antennas, but just space them out as if you had a big one. So this is what's known as an interferometer. Okay, there are a lot of downsides to that, but what you get is more resolution by just spacing out your antennas further apart. Okay, so what does radio data actually look like? Okay, so interferometers work on the principle, as the name suggests, of interferometry. So it's basically a wave hits the detector, it gets made into a sine wave, okay, some waveform. And what you do is you take the other signal that hits the other detector and you do what's called a correlation, where you basically add the wave signals together. Okay. Now with wave signals, there's two things that you measure. There's the amplitude of the wave, so it's the height of the wave. So you can think about how much of a radio signal is actually hitting the detector, the strength. But then there's this neat other property that you get, and it's known as the phase. So the phase is how lined up is one waveform with the other. So if it's perfectly in phase like this, where you have the peaks lining up with the peaks and the troughs lining up with the troughs, they will do what's called constructive interference. So the peaks will get even bigger and the troughs will get even shallower. Okay. However, if they're completely out of phase, you have the peak of one wave is in the trough of the other. So when you add them up, they destructively interfere and you get no signal. Okay. So the basis of this is if you had a two telescope array like this, where you have two antennas, your radio image is going to look like this, okay? It's just a fringe pattern. This is what we call it, bands of light and dark, okay? So this is not too fancy with just two antennas, but what can we do with the two antennas? We can change the distance between them, okay? So if we were to do the same observation with two antennas, but space them out a little further apart, this is what you get, a fringe pattern, but the fringes are more closely spaced together. So you get more detail out of your image if you space them apart. However, with everything in life, there's always a drawback when you change something. And here it's hard to notice, but it will become clear in the next couple slides. What you get when you space them out is less overall brightness, okay? So your brightness decreases, but your detail increases, okay? So there's a balance game that you have to play with interferometers to be able to get enough brightness so that you have something to look at, but enough detail so that it doesn't look all smudgy. Okay, so what I've done in the past couple days is ran some mock data for you guys on this picture here. So of course, everybody should know this. This is Saturn. Okay, so I'm going to use this as a model image to show you what radio data looks like with two of the most popular interferometers here in the Americas. Okay, so this is going to be our model image. We're going to assume that Saturn is much further away than it actually is, somewhere outside of our solar system. And we're also going to assume that Saturn is just outputting this amount of radiation, this picture, into the radio. Okay, Saturn does have radio emission, but it's not like this in the visible. I'm just going to use this as a model. Okay, so I'll put the model up there so you can use it as reference. The first array that I'd like to show you is the VLA, the Very Large Array. Okay, yeah, astronomers are not great at naming things. That's okay, okay, but it's the Very Large Array, and it consists of 28 total antennas, okay? So remember back to the previous slide where two antennas make a fringe pattern. Well, you can make a fringe pattern out of any two combinations of any of these telescopes, okay? So you can combine these two on the end, the next two in the line, the next two in the line. All the unique combinations of two antennas will get you many, many baselines. These are what they're called. So for 28 antennas, it's almost 400 different fringe patterns that you can get. And then you combine all those together to get your image. Okay. Additionally, facilities like this one and the next one that I will talk about actually situate something that you can move the telescope. So at the VLA, there's 3 train tracks next to each one of these arms where they can pick up the telescopes, put them on the train tracks, and shove them all the way down to further space the telescope apart. So you can actually change the resolution of your image by taking all the telescopes and putting them further apart. Okay, so in its most compact configuration, something like this is what you would get when you observe Saturn, assuming that Saturn is just dumping out a bunch of radio. Okay, so that's what that looks like there. Okay, so you see it's low resolution, it's kind of blobby looking. You get a lot of brightness out of the image, but not much detail. Okay, so next picture I'm going to show you is an observation with the VLA done in its most extended configuration. So if you spread the telescopes out further and further apart, this is what you're going to get instead. So the overall brightness of the image is heavily decreased, right? You can just see how bright this image compared to this image. But with the bottom image, what you get is what we call all the sharp features. Okay, so we get all of the things that transition from light to dark very quickly. So things like the ring structures or the very edge of Saturn really pop out here in this image. Okay, and the power of interferometry is that you can take data multiple times and then just combine it all afterwards. Okay, so if we add these two images together, you get an overall image of what Saturn would look like if it output a lot of radio. Okay. However, with the VLA, unless you have a lot of time on the telescope to take a lot of data, what you get is these big fringes of light and dark. So you notice how the edges of the picture in the vertical sense has a lot of dark, and then the middle has a big white band. This is what's called artifacting, and it's what radio astronomers try and mitigate as much as possible. And that's just due to the actual layout of the antennas on the Earth. Okay, so what I'll show you is the array that my data comes from when I do my research, and this is the ALMA interferometer, the Atacama Large Millimeter Submillimeter Array. Okay, it consists of 66 antennas, so almost 3 times as many antennas, and it's located in Chile, northern Chile, up on a very high plateau. I think its altitude is like 5,000 meters or something. It's very, very high up. Okay, and the same thing with the VLA, there's a little transporter truck, so it can pick up an antenna and move it across the plateau. So at its most condensed, antennas will be, 12 meters in separation, but at its most extended, between antennas, it can be almost all the way up to 2 kilometers apart. Okay, so if we do our same studies with our mock observations, here's what ALMA would see in the most compact configuration. So a lot brighter of an image than the VLA. That's just because you have almost 3 times as many antennas. And then here is what ALMA would see in its most extended configuration. So a lot less brightness, but a lot more detail. So we can combine these two together, just like the last one, and we get an overall picture of what Saturn is. Okay. So all of these observations that I've shown you that I've mocked up, right, used a program and did some synthetic observations, this was with 10 seconds of on-source time. Only 10 seconds. Okay. What you usually do is you ask for more time. So not only do you ask for more time, you can ask for many more configurations to get more or less the detail that you're looking for with these arrays. Okay. And there's one last trick up the radio astronomer sleeve that we can use for interferometers, and it's known as Earth rotation aperture synthesis. A lot of fancy words, but we basically don't need to do anything at all with this technique, just because of the way the data works. Okay, so what do we get from interferometers? We get an amplitude measurement, so how much signal is hitting the detector, but we also get that phase information. Okay. And because the Earth rotates, your source on the sky is going to rise and set, just like anything else. Okay, and when you look at it and your wave fronts are moving across the sky, your phase is constantly going to be changing. And so you're getting new information by the Earth just rotating. So what this does is it doesn't give us an increase in brightness or an increase in detail, but what it does is it lowers the noise floor of the image. So images that look very noisy can be solved by just taking more data. So it's natural across all of astronomy that this happens, but interferometers are real key with this. Okay, so an example would be if you have this spiky waveform, but your noise is very high, it's hard to tell that feature in your data. But if you just take more data, the noise floor goes down, you're able to see the features in your data. Okay, so that's a little bit about radio astronomy and why it's used. So I'm coming up to my 30 minutes of estimated time. So what I'm going to do is I'm going to end my presentation with something I think is probably the most beautiful piece of astronomy I've seen in the past 5 years or so. It is from a simulation. It's called the Star Forge simulation. You can look it up at home. It's on YouTube. But it's a simulation dealing with cloud scale physics. Okay, so it's a big molecular cloud that was allowed to progress through. It has all the relevant physics that we deal with in the star formation world. And we can see a little bit about what that looks like. So I'll play this out now for you, and then we can see how that goes. So we start with a big cloud of molecular hydrogen, and we let it evolve. So higher density regions will start accreting material from its surroundings. You'll see web-like structures start to develop. As soon as you see some of these bright little dots, those are going to be protostars that are forming out of the filament structures. So you can see a little bit of them at the top there. And as it evolves a little bit further, you'll notice that something happens with all the stellar populations. takes a little while. Space doesn't go very fast sometimes. You'll start to see them now. You can see them up at the top a little bit. It'll become very apparent soon once we pan down. So these are the outflows from protostellar sources. Mind you, these are not observations, this is simulations, but it's realistic simulations of what happens at the center of these giant molecular clouds. So we have big outflows. So if you wanted to know how powerful protostellar outflows are, they're very powerful. Okay, so they end up spitting all the material back out. Excellent. So what you'll notice is that higher density regions will continue to become higher and higher density. So the concentration of stars in one area will suck up all the things from its surrounding area. So you get higher density regions. These are known as hub regions where all the stars are starting to gather. And if we were to be able to zoom out a little bit, you'll see that all the empty space in the molecular cloud is becoming emptier and emptier. These are known as voids. Okay, so star formation happens on hubs and filaments, and then the voids get left behind until stars end up pumping out a lot of radiation, and then they'll blow back that material out into the interstellar medium. So yeah, pretty fantastic. I think at the end of this video as well, there is a supernova that goes off. So a supernova is what a star does at the end of its lifetime. Depending on certain conditions, it will collapse down into the core. The core can't collapse any further, so all the incoming material will end up bouncing back out, and it's going to be a huge shockwave that propagates out. So I'll let that conclude my talk there. There it goes. So that's super powerful. Very, very fast shockwave. It's a compressive thing. It shocks the interstellar medium. And this is usually where the star formation cycle repeats itself. The star formation timeline that I showed you goes from gas cloud to star, but this whole process is a cyclical thing. Okay? Yeah, Star Wars. Excellent. Perfect. Excellent. All right, I'll finish it there. Thank you very much. I'll play the video in the background while I take questions. Perfect. Yes?
How long does the process usually take your 6 that needs to be done?
Great question. So there was actually a little timeline. So I can pull it back up here for you. So the process usually starts, what we say time 0 is where we get to the dense core stage, okay? So things that might actually have a chance to become stars. And so the dense cores all the way up until protostars is around 10 to the 4 to 10 to the 5 years. That's 1,000 to 10,000 years, okay? So in terms of astronomy scales, quite short, okay? Going from protostellar to sequence, about another 10,000 years or so. So the whole process is in terms of the 100 to million years to go from molecular cloud down to stellar cores. Yeah. If you think about the age of the universe as being somewhere in the neighborhood of 14 billion years, it's on the order of a % or so. So quite small. Quite small. Yeah. Great question. Excellent. Yes?
So I understand that lots of stars up there are young stars. So are they formed at the same time?
What are, sorry?
Double stars?
Oh, double stars. Yes, this is a great question and something that deals with my research specifically. These dense core structures here, as you can see, the scales of which are still quite large. So for those of you who know, 1 AU is the average distance between the Earth and the Sun. Okay, it's 1 astronomical unit. Okay, so this is 10,000 of those distances is what you get from this overall structure. So in terms of stars being born in terms of groups of stars, either binary or tertiary or even more, it is the case that these structures here end up fragmenting out to multiple star systems. And what we know from the past 20 years or so in this field is that most stars will develop as binary or more systems. So it's very rare that you would get a star system that ends up birthing one single star. It does happen, but we think at this point that most stars are born at least in a pair or more. So there's a lot of research that goes on into how these clumps fragment down into smaller and smaller things and how individual that process is. So that's a great question. Yeah, excellent. Yes.
What causes the outflow? Is that spinning towards the center?
Yes. So this is kind of a running joke in the astronomy world is whenever you want to ask a tough question, you ask about things that astronomers don't know much about. And the main topic right now, or in the past 20 years, is magnetic fields. So magnetic fields are something that are very hard to measure out in space. And we think they actually have a very large contribution to many of the things that have gone unexplained. So for example, some of the outbursts from black holes are due to magnetic field interaction. So when you have a lot of matter crashing down into some disky-like structure and it's feeding in, that's when you usually get magnetic field interactions that drive outflow along the perpendicular axis. So to answer your question, magnetic fields. Yeah, exactly. Yeah, it's a big topic right now in many branches of astronomy. Yeah. Excellent. Yes.
So the simulation showed all of this hydrogen gas.
Yeah.
And then the stars started to draw themselves together.
Correct.
Do they crash into each other at some point? Like what happens when they get so dense?
Absolutely, yeah. So many of those interactions, you know, the gravitational force is an infinite force, right? So when you have higher density matter, it tends to suck things into each other. So yes, you do get stars that crash into each other, especially in star-forming systems. However, those can be quite violent, but most of the times a direct collision is not really what happens. They'll fly by, they'll come quite close, but they'll end up dispersing back out. So it just depends on what we call the impact parameter, or how close two things get. But a lot of the time, what can happen is if things get too close, it ends up being pretty violent. So those things, they end up crashing into each other. Now you get nuclear processes like hydrogen fusing and different interactions with that gas. And it ends up creating things that naturally disperse clouds back out. So there's a little bit of a balancing act with that. But yes, this is something that happens all the time in star-forming regions. Things just come crashing together. So yeah. Yeah, it's very turbulent, very crazy, very chaotic. Yeah, excellent. Yes.
So there's no like physical like part of this star, like a coldest gas.
Pardon?
Like with the stars, is there any like physical like thing that defines it, or is it just like gas or like?
So what defines a star specifically is what we know as a main sequence star, is what we usually, you know, associate the term star to. And the term star usually refers to at least some type of nuclear process inside. So yes, it's all gas, but that gas undergoes changes as the star evolves. So what we classify as a main sequence star is when hydrogen is hot enough so that it can then start fusing into helium. And then a red giant, for instance, would be going from helium into the next stages. So this kind of chain process. So there are some nuclear processes that happen all the way back to the protostellar stage, except they're not full on hydrogen fusing into helium yet. So yeah, I guess hopefully that answers your question. Yeah, excellent. Yeah.
So everything that you've spoken about today is using, I understand it as light to do the measurements.
Correct.
So we talk about hydrogen and helium. How do we know that? How do we know gases are involved?
Great question. So there's a couple answers to this. How we measure different things comes in kind of two forms. So really the only information that we get from outer space, unless something lands on Earth or we go out to it, is in the form of light. All the information that we get. But it's not just light. in its basic form, we actually can do a lot with individual pieces of light. So what we do to figure out what the chemical composition of things are is we determine some electronic transition in the molecule. So for hydrogen, for instance, if you excite a hydrogen electron, right, the electron's orbiting the proton, if you excite it up to a state and it falls back down, the conservation of energy comes into place, and it emits a photon or a piece of light with a specific wavelength. And so, for instance, this molecular hydrogen here is what is known as 21 centimeter emission. So we look for a specific wavelength of light that we know only comes from the transition in a certain molecule. So this is the same thing when we do planet atmospheric composition. So the James Webb just detected, signatures of water in a planet's atmosphere. This is where we use specific wavelengths of light. And if we know, if we look for that exact same signature, it's like a fingerprint. And so we know what things are made out of because we can do what's known as spectroscopy. So this is the big thing. Yeah, excellent. Okay, Calvin, is that good?
Oh, yeah.
Excellent. Yeah, if we don't have any more questions, I'll end it there. I'll play the video again if people do want to see it. But thanks for joining me today. Feel free to come up if you have any questions as well. I'm more than happy to answer them.
I just had one question,
Yes.
and I never made it past Science 14,
Fair.
but I'm in.
Okay, well, at least I can hear you, Amy. Oh, it looks like we're on now. Okay, that's great. I can see that my picture is appearing in the FDAO stream, and it's great that you're on, Amy. Welcome to What's Up for May 27th to the summer solstice. And we call it What's Up because we're always interested in what's up in the gift shop, and the gift shop's an important part of our operation because it helps raise funds for our education programming. So it's guilt-free shopping. And so Amy, I'm going to put you on the spot since we actually have your audio here and just ask you if there's anything that comes to mind right now. You probably don't have anything prepared from what last time I talked to you, but is it anything that really captures your attention right now in the gift shop?
Well, if you're on the hill, one of the things that captures my attention is that we have a local ice cream company called Hazel's. We have their ice cream bars that are available for when people are on the hill. And in terms of products, we have some just fantastic books in right now, one of which being Bob McDonald. There's feedback there. We have Bob McDonald's new book in the gift store. But I would like to, Don, if it's okay, take just a quick moment to put in a plug for the Passport to Science that we are partnering with 10 other science facilities in the Lower Island where kids can get a passport essentially, and over the course of the summer, they can get stamps when they visit different science centers and get a chance to be entered into a prize at the end and get something just for participating. So those passports are available at any of our partner sites. And the science sites that are taking part are the Victoria Bug Zoo, the Shaw Center for the Salish Sea, us, of course, Victoria Butterfly Gardens, the Raptors in Duncan, the BC Aviation Museum, Dino Lab, Nanaimo Science, and Butterfly World Coombs, as well as Swan Lake Nature House. So it's a fantastic group of science sites, and I recommend that people get their hands on a passport or contact us if they're local and need a passport dropped off to them. We'd be happy to do that, and can't wait to see everyone on the hill.
That's great. Thanks, Amy. And also, we really need everybody's donations now. We're waiting for grants to come in. So if you're inclined to give us a tax deductible donation, we'd sure appreciate it right around now. And so that's really great. Now, is somebody as old as me allowed to get stamps and maybe win, or is that just kids?
Well, I think you could get stamps, but I don't think you could get a prize.
That sounds really great, and I haven't been to all of those places, but I know there's some real favorites there, such as the Swan Lake Nature Center and a few others. And I didn't know there was a butterfly zoo in Coombs, so that is, I don't know if that's new or not, but that's great.
Yeah, no, that was new for me as well. Yeah, that's yeah. So I'm excited to go up to see that one too.
Yeah, you can go get ice cream up there and see some butterflies. So cool. Okay, so let's continue on with talking about what's up in the sky for May 27th to the solstice. And just talking a little bit about summer here. The summer is typically said to begin on the summer solstice, and this is when the sun reaches its maximum northern position. Also, as you all know, the longest day and the shortest night. This is when the sun reaches its maximum northern position. And also, as you all know, the longest day and the shortest night when the sun and the sun at midday its highest northern position. However, the also, as you all know, the longest day and the shortest night when the sun and the sun at midday its highest northern position. However, the also, as you all know, the longest day and the shortest night when the sun and the sun at midday its highest northern position. However, the also, as you all know, the longest day and the shortest night when the sun and the sun at midday its highest northern position. However, the also, as you all know, the longest day and the shortest night when the sun and the sun at temperature is rise, but that's actually not necessarily that you can get a pretty bad sunburn even before we're into the warmest days of summer. And so today, May 27th, the sun rose at 5:20 a.m., very early, and will set at 9:01 p.m. Pacific Daylight Time. And so notice that it's now setting after 9 p.m. And on the solstice, the sun will rise at 5:11 a.m. and set at 9:19 p.m. So about 18 minutes later than tonight. And if you can see the sunrise or sunset points from your home, note how far north they are and compare those points with the winter solstice points. And identifying these points on the horizon to mark the seasons was a very common practice in cultures around the world for thousands of years, including indigenous cultures here in British Columbia. And that's not that widely known, but they certainly did the same sort of thing and often designated a certain person to track the seasons. So let's talk a little bit more about what's up in the sky here. And I'm going to start by sharing Stellarium. And we're going to see what it looks like for, if I can just move things out of the way here. This is just after sunset tonight, so this is about 9:30, and we can see Castor and Pollux, the stars in Gemini, the twins. And incidentally, a little bit of trivia, both stars here, Castor and Pollux, are actually double stars. So it's kind of like a double-double. So there's a pair of points of light that we can see, but each star is in fact a pair. And you might recall that just a couple of weeks ago, these stars are pointing pretty much right at Mars. But look at how much Mars has moved in the sky since that time. And Mars does move quite noticeably in the sky from I wouldn't say necessarily night to night, but every couple of days. And so you can notice that it's doing this little dance here with Venus in the sky. So so Mars is actually getting fainter because we're moving away from it, but Venus is getting closer. And as it gets closer, it's actually getting brighter, as you would expect, because light falls off as 1 over the square of distance. And so if it's closer, it's going to get brighter. But the phase is changing, and so it's turning into more of a crescent shape now. And so it'll look more and more like the crescent moon rather than a fuller shape. So we have kind of competing effects here with Venus getting closer and brighter owing to its distance, but also less of the illuminated surface being visible. So it's going to be sort of getting slightly brighter, but more or less maintaining its brightness over the next little while. And in the morning sky, you'll be able to see Saturn down in the southeast, and Jupiter is just still kind of lost in the twilight glow in the early morning sky, more or less due east in the morning. And so today marks first quarter moon, which is when we see half of the moon illuminated, and that always causes people some trouble because they call it the half moon, but in fact we call it the first quarter moon because the moon has completed the first quarter of its orbit around the Earth. And so these major phases of quarters are about a week in length. And full moon in June is early this year on June 4th. And I'm going to try to advance the time here in Stellarium. And let's just move over here. And we're going to go to, let's skip back a month. Going to go to June 4th. And we're going to move over to a different part of the sky and look for the moon coming up. And it actually doesn't come up until fairly late. So it's actually almost 11 o'clock at night. And there you can see it peeking over the horizon. And so it's actually unusually close to the horizon at this time of the year. And I'm just going to put some markings on the sky here. And what we're going to see is the plane of the Earth's orbit. And so this is the plane, again, that the Earth moves around the sun. And we can see that the moon's orbit is tipped a little bit. It goes a bit above and below that line sometimes. And this distance is about 5 degrees. So that's about the furthest south it gets. And so if it was like right on that line, you can see it would be higher above the horizon, but it's not. It's quite low down. And so this is a great time to actually, if you can stay up fairly late, and I'm just going to move this out of the way, this is a great time to look for something called the moon illusion. And this is something that's not entirely understood, but the moon actually appears bigger when it's closer to the horizon. And so if you were to try to remember the size of the moon, the visual appearance of the moon to your eyes, when it's this close to the horizon, and try to remember where it is and how it looks 6 months later in December, you would actually think that the moon looks a lot bigger at this time of the year. But if you were to actually measure it, it isn't. So just to try to get away from this effect, you can try a few different things. And some of them involve, well, I guess, a little bit comedic. One of the things you can do is turn your back to the moon, bend over and look between your legs down by your knees and have a look at the moon. And some people think that the moon illusion goes away when you do that. Another thing you can do is you can take like a toilet paper tube and you can look through the toilet paper tube at the moon and try to actually close your eye before you look through the tube so you don't see too much around the moon at first. You don't want to bring it in like this, and so you're already looking at the moon. And so you're just seeing a little bit of the horizon with it and see if it looks any smaller. Next, if that doesn't work, what you can do is get a paper tube like this for paper towels and try the same thing. Look at the moon with even less of the horizon and hopefully none of the horizon, and then see if it looks any smaller. And so this doesn't work for everybody, but it does work for some people. and it's kind of fun to look at and to think about. And we think this might have something to do with maybe a survival instinct, maybe things closer to the horizon we needed to focus on a little bit better with our brains or something. Maybe there's a tiger lurking over there in the distance. But I don't know why it works with the moon, because we should know the difference between a tiger and the moon. But nevertheless, it does appear that that actually seems to happen for most people. So there's something else I want to talk about right now. We were just talking about the sun, and I was going to talk about constellations, but instead, I think what I'd like to do is talk a little bit about the sun up in the sky these days, because there's lots of bright sunspots visible. And of course, this is not something you want to look at with your unprotected eye. You usually need a special solar telescope with very expensive filters on them and so on. But the easiest way, if you don't have access to that, is to actually try to build your own solar filter, or pardon me, solar projection. Let me straighten that out. A solar projection system. And what you can do is build what's called a pinhole camera. And so hopefully you can see this on the stream. And what you can do is take a card and poke a little hole in it and put another white card on the ground and make an image of the sun. And these sunspots that are visible are big enough that they should show up in this tiny little disk. For myself, what I like to do is, instead of a white card, which is hard to make a clean hole in, is to get a piece of tin foil and then take a pin, like a sewing needle, and poke a hole in the tin foil, and with my back to the sun, hold that up and let the sunlight come down onto the white card or piece of paper on the ground. So you just need, it doesn't have to be a card, it can just be printer paper or something like that on the ground, but you should be able to get a nice image. So see if you can see these large sunspots over the next little while. And I think what I'm going to do here is, if I can try to find this, is maybe show you. Amy, does this show up, this large sunspot on the stream?
Yeah, I can
You're
see
still
it.
there? Yeah,
I can see
okay. So this was taken near the maximum of the last solar cycle, and you can see that this is a very large sunspot, and it's we think that there's a very large one that's going to be visible in about 10 days. We don't know how big. It's a little bit hard to predict, but what they're able to do is they're able to detect a very large sunspot that's formed on the far side of the sun by essentially looking at acoustic waves, vibrations moving around the surface of the sun. And so there's something over on the far side that's disturbing the pattern of these acoustic waves, and they've inferred that there's a large sunspot there. So as the sun rotates around in 10 days, we're going to get a view of that area, and hopefully it's going to be a very interesting sunspot. Okay. So let's move on to talk a little bit about something else. And I think what I'd like to do is talk about the supernova that's just been detected. And for that, I'm going to put on the constellations here, because I'd like to show you the area in the sky where this is visible. And I'm just going to change the time here a little bit. I'm going to move it back to today's date, and bear with me as I fumble a little bit with the night sky here. And if we were to turn around and try to look at the north, you see we're looking at the west here, and we're looking at the north, and look up, you can see the Big Dipper over here. You can see the bowl of the Big Dipper. It looks like it's pouring out here, and we can see that you can see the handle of the Big Dipper up here. And the galaxy that is the host of this supernova is very close to the handle of the Big Dipper. And with luck here, I'm going to be able to turn this on. And in fact, there it is, the Pinwheel Galaxy. And this is not something you can see with your eye. And so if you don't have any optical aid, you can maybe just go out there and look for the location and think about this galaxy sitting out there. But it's a face-on galaxy. Our galaxies are kind of shaped like pancakes, at least ours, the type we're in, is like that. And this galaxy is like that as well. And we're seeing this one face on. And so the supernova is one of the stars in the galaxy that's gone off and currently is putting out about as much light as the entire galaxy. And this pinwheel galaxy contains about 1 trillion stars. And that's kind of a hard number to imagine, but if you were to try to count up all of those stars at 1 a second, it would take you about 31,000 years to count up all the stars that are in that one galaxy sitting out there. So there's a little project for you. And if you have, say, a 6-inch telescope, 4 to 6 inch telescope, and a fairly dark location, you might try to find this galaxy at least, if not the actual supernova, over the next little while. And it's good to try to do that in the next couple of days, because as the full moon comes on around June 4th, even though it's low down, it's going to cause the sky to brighten, and it might make it hard to find these fainter objects. So I think that's it for tonight, but I would say if you don't want to build a projection system like I was describing, go to spaceweather.com and monitor what's happening with those big sunspots. So that's about it for now. And Amy, do you have any questions or comments before we sign off here?
No, I was just gonna say, we had the solar scope up the other day, and it's just, it is an amazing time to look at the sun right now for sure. So, I thought what a great craft project to to work on. It's yeah, we have some of those. I forget what you'd call them, but the cardboard solar viewers, right, where it does exactly what you're describing, and it is it's just incredible how clear the sunspots come through.
Yeah, and one of the problems with just putting the piece of paper on the ground is that there's stray light that comes in. Sometimes it's a little bit hard to see that. So it's nice to actually maybe put it into a big box. The longer the better, and with maybe the tin foil on one side and the white paper on the other side of the box on the inside, and so you get more contrast. So when are there any opportunities for people to come up and look through the solar scope or use these pinhole cameras?
So right now we're looking at our summer hours will start on July the 4th. We'll be open 10 to 3 Tuesday to Saturdays, and there will be opportunities in there, but people should really stay tuned to our social medias, which is we're at Friends DAO, of course, on Instagram and on Facebook, as well as our website, centeroftheuniverse.org, to see which days, if we're going to have the solar scope out, we will post in advance that that's going to happen so people would know.
Okay, that's great. And my understanding is we're really just getting this solar scope going. Is that right? So in terms of bringing it out regularly for people, it's not something that we've really done a lot in the past.
Correct. It was out at the last star party a couple of weeks ago because, it was just so bright early on. But then we only get a sun before the sun sets, really. And but when we can, we're trying to get more people trained on it. So
Okay, that's great. And I think I'm just going to try to maybe show one more image here if you can put up with
yeah,
me
that would
for
be
just
great.
another
Yeah,
second or two.
for
But
sure.
there's there's some really terrific amateur astrophotographers out there who are taking pictures of the sun, and they have special filters very often on their telescopes. And I'm going to see if I can find an image made today. Here we go. I'm going to try to share it, and just bear with me. And it's a bit of an animation as well. And this is the sun just in a very narrow color band of hydrogen alpha, and it's showing the appearance of the surface of the sun today. And it's really quite amazing, all the detail you can see. You can see prominences, which are basically ionized gas following magnetic field lines on coming up from the side of the sun, and we see them as these dark lines in silhouette. And we can also see these flare regions, which are usually associated with these sunspot groups. So what appears maybe dark at visible light, as I was showing you in the other image, is usually surrounded by these very intense areas here. And these areas can erupt and actually throw charged particles towards the Earth and produce the northern lights. So that's something else to stay tuned about at this spaceweather.com site is announcements about Aurora. So there you go. So lots of exciting things happening, and I think there's going to be plenty to see during the summer hours in July and August. So
Yes, for
okay.
sure. Thank you so much, Don, and thank you to everyone for tuning in.
Yeah, thanks everybody, and see you next time.
Thank you.